I'm very happy to introduce Lorenzo Lelli, a director at the firm INGENI, which is a structural engineering firm in Switzerland. Lorenzo, the floor is yours.
So good morning, everybody. Thanks for giving me the opportunity to talk today. I will show a study that actually we did a few times ago, but still it has some approaches that I think that can be useful on everyday fire performance analysis. So it was the fire performance analysis of the building, which is shown in the picture here, that are the new headquarters of JTI in Geneva, Switzerland, and just a few figures about the building. It is a 10-story administrative building which was designed by SOM, and we shared the structural design together with them. We were responsible for the fire performance design, and it is now completed. As you can see in the 3D model, which is in the middle, it is composed by a 3D steel truss that is supported to itself, and these the main trusses are aligned with correspond to the facade, so the internal and inner and outer facades, and all the stories are supported by those big trusses along the facade. Of course, it was necessary to make fulfill at least the R90 requirements according to Swiss regulation. Why, on the contrary, we choose the natural fire approach? There are basically three main points. If you look at one typical floor, which is shown there, you can see that there are two major fire compartments of up to 2,800 square meters that are completely glazed in the perimeter, with the only exception of the compartment partition that at the frontier. The exploitation was an open office spaces. So basically we have a thermal load which is not so high. We have the contribution of the facade, which has the advantage in terms of fire performance that collapses at a certain temperature, and while collapsing it makes of course there is a new air intake inside of the compartment, so the temperature gas gets lower, even though there is a new oxygen which is introduced to the compartment. The advantage of lowering the temperature is bigger, and we will see later. And also is also a building for office which had certain story height which is considerable, because we are almost close to 4.5 meters, considering also the false ceiling, which is permeable to air. So the fact that having a big volume helps in the natural fire analysis. So how we did with this analysis, there are several guidelines which are now more or less consolidated in quite all the countries about how to model the facade behavior. Generally, we need to make they advise to use a stepwise system, so which corresponds to make a certain percentage of facade that collapses sometimes close to 300-400 degrees, and then to let collapse the remaining part, or keep at least at 20% anymore at 500 degrees. It is generally admitted that beyond this temperature, there is basically no glazing that can sustain the fire temperature, the gas temperature. So this, I think, something that is very interesting in terms of resistive materials, in particular steel, which is we know that 500 degrees is a typical temperature where there is the complete change of the mechanical behavior, mechanical properties. So we made this simulation with ozone for each scenario, or at least for what we define as the typical, the critical scenario, the critical compartments. summing up, adding up the 5 scenarios, and then obviously we choose the one that will be the most critical. As you see in the diagram here, you can see that as long as we reach as long as the fire starts, we reach the temperature in the compartment increase, reaching 300 or 400 degrees depending on the scenario. Then there is a step down which corresponds to the entry of fresh air, and then it raises up until the next threshold, which is the 500 degrees. Then we already have most of the thermal load which is has been burned, so we will not only we have again a fresh air that reduces the temperature in the first moment, then we have the descending branch. The base geometry, so the typical floor is composed by a typical bay 12 meters by, times 15.76. That's generally repeating. The strategy was to protect the edge beams in order to develop the membrane behavior, and to leave unprotected the primary beams, that are the blue ones shown in the diagram, and the secondary beam that are not shaded are, well, of course, not protected as well. There is the composite floor is made of a metal deck plus the topping of concrete with a ribbed slab plus a topping of 80 millimeters. And to model this in SAFIR, there are 3 steps. First, there is a first analysis that need to consider the mean thickness, which means taking the mean value with the ribs. And this is necessary to determine the correct thermal, thermal massivity of the slab itself. Then a second modeling is related to determine the temperature variation along the section, and in this case you need to consider the full thickness because you need to determine the temperature all throughout the slab. And the third one, which is the final static analysis, we consider only the effective membrane thickness because it's the one that corresponds to the isotropic or orthotropic membrane, so the area without the ribs, which is obviously conservative, but on one way, because the one without the ribs, but also we can point out that since the ribs are the ones that are exposed to higher temperature, more or less in fire terms, this is quite negligible. So fire analyses are quite classic for SAFIR. First of all, we have a thermal 2D analysis of the section, considering steel plus concrete. Then there is the 2D thermal analysis of the shell alone. We define the temperature variation at each time step, and then they are composed on a 3D model, in which, for example, we set up a 5-bay 3D model to run the analysis. And of course, the mechanical parameters are evaluated at each time step based on the temperature distribution. Just a few snapshots of the results. The peak was more or less situated at 75 minutes for the critical scenario for sure, but also all the other scenarios were close to this duration. So as you can see from the deflection diagram, there are the primary beams, that are the one perpendicular from facade to the other facade, are more or less with a quite regular deflection, which means they're very close to an elastic behavior. And on the opposite, the secondary that are parallel to the facade can already, from here you can see that the deflection diagram is not so linear, so which means that some of them may have reached plasticity in some areas. And of course, hope you can see from the screen, there is the effect of circle that you can see shows that there are somehow 5 membranes that are developing during the fire. At end of fire, so at almost 150 minutes, there is the descending branch, so the phase. Since the primary beams were more or less in the elastic, they mostly recover up all the deflections, so they are now quite they're quite to the original geometry. And on the contrary, the beams that have reached plasticity or they went through plasticity, they did not recover completely. This maybe is more clear when you see the diagram of the deflection. So the violet is again the primary beam, so it recovers more or less the initial deflection, static deflection. And the other two elements, either slab or secondary beams, they do not recover once they have passed through the plastic phase. In terms of membrane forces, at start we have this typical printout from membrane force distribution in SAFIR. And then when we go through the peak, you can see that the tensile action takes place, and that's shown by the red elements, the red arrows. And in the cooling phase, which is also important to assess during the natural fire approach, there is, due to the recovery of dilatation, there is this transfer of forces that comes to the beams that are still have some major stiffness, which in this case was only the primary. So there is a concentration of compression forces located at the primary beams area. Again, this is also visible by a diagram of that pointing out some areas. So the peak is between 60 and 80 minutes. So you can see there in this area, in this time shift, in this time range, you have all the elements are in tension, and then there is a switch going to the compression phase. Also, which is now less peculiar than once with the time we did the analysis, but we have, as you may have seen from the shape of the building, we have some areas that do not have the fully orthotropic geometry. At the time, SAFIR, the rebar bar, where the rebar axis orientation was referred to the local reference, so we had some minor distortion of the stress path, and of course from several releases on, because this analysis dates from 7 years, so there has been several new releases that amended this issue by giving the possibility to orient to align the rebar to a global model, so get or a local model, so can get rid of this problem when the geometry is not regular. To complete the analysis, it is always necessary to couple the fully engulfed scenario with a localized fire, because both can be critical, and both can when we get rid of, when we decide to get away from the ISO 834 curve, we need to cover the more that we can get of plausible scenarios. So for this project, we choose to use the ASEMI fire model described as it is in the Eurocode, because it was suitable for the geometry of the compartment. The flame was expected to touch the ceiling, and there is a specific routine in SAFIR that can help to do this analysis. So I won't get long on this, but the routine generally determines the time distribution and mechanical properties at each time step for every single finite element of shell and beam. And so when we consider so it can be applied to the same 3D model that was used for the fully engulfed fire. And obviously there is a different criticity. As you can see from the diagram, we can reach locally higher temperatures compared to the one of the full engulf. Of course, there isn't the effect of the glazing facade as long as the fire is not located close to it. So we have more or less 300 degrees of difference, which are more severe for the steel. But of course, as long as you get away from the fire, the steel is less exposed to this temperature, so it increases in capacity. So the redundancy of the system around can make the system stable, which was the case for the analysis we did. So to summarize, this is again one of the typical floor where you can see the savings in terms of intumescent paint, which is the contrary. There is what is shaded in red and orange are the intumescent paint that was kept in the execution project, and what that means all the other elements were without intumescent paint. So as I said before, all the spandrel beams are protected to ensure that the membrane behavior takes place. The area close to the holes, for the same reason, are also protected. The spandrel, the beams close to the holes, main holes, also have to be protected for the same reason. And also, we protected those at the corners in order to have as much as we could have an area where we can develop right here a membrane behavior for this entire surface. So we need to protect these two primary beams. And just to also to complete the strategy, there are some secondary beams that are also protected because there are those that are located over a partition wall, which is the separation of the two compartments. So in order to ensure that the displacement under fire were low and will not touch the wall, and so makes pressure and damage the walling. So to maintain the hypothesis of the full compartment, we need to protect these 3 elements here and 3 elements that are located there. So just in conclusion, the analysis that are carried out here show, considering the membrane behavior, allows obviously a significant reduction of fire protection by mean of increasing the reinforcement ratio. We expected, we noticed 20% of increasing, so in the reinforcing ratio for the slab. Obviously, this increase is widely covered by the savings related to intumescent paint. So this is, I think, it's an approach which in any project will be interesting from a simple economic point of view. And in general, which is quite obvious, the natural fire approach is worthwhile when we have fully glazed or with a high percentage of glazed surface buildings. As I said before, there are automated routines for localized fire in SAFIR that can be applied easily in the same model that we use for generalized fire. And as I said before, the issue with the orthotropic non-orthotropic meshes was solved now in the latest 2 or 3 latest issues of SAFIR. So this is something that can easily take in consideration for any other analysis or any complicated mesh. So that's more or less it. So that this a few pictures of the building completed or in completion, and I'm happy to answer to any question if you have.
Thank you very much, Lorenzo, for this great presentation on a great project. As a comment, it's interesting to see the model of tensile membrane action in a panel that has an irregular shape, right? Because often these are rectangular panels, and here we have this irregular shape, but the analysis showed that we could still work by protecting only the peripheral members, right? Do you know, you mentioned an increase in the reinforcement ratio. I don't know if you have the numbers on top of your head, but do you know approximately how much reinforcement there was in those slabs?
The typical, I don't think it's shown there. No, maybe in the, I think we ended up with a diameter of 10 millimeters per each 15 centimeters instead of what we would have used would be 8 maybe because I think we're close to this 20% increase if I'm not wrong.
Thank you. There was a question about your 5 base model, when you showed the deflections of the beams, I think it's just a few slides later. Yes, that might be this one. Did you have an idea why? So in the secondary beam, the red curve, right? So it goes back up when it starts cooling, I guess, but then there is kind of a wave behavior, right? It goes back up a little bit and then it stabilizes at a little bit larger of a deflection, but that's not observed in the primary beam. Do you know why?
No, I think that this is linked to the fact that the secondary beam, due to its stiffness, was due to its low stiffness compared to the primary, wasn't able to had to follow the slab deflection itself. I would say. So I think the two elements, secondary beam and slab, since they were in this membrane behavior, where I think you need more. Was not so. How can I say? We interpret this way. So we thought that since there was no much recovering stiffness in the beam, they weren't able to. They were mostly the system slab plus secondary beam was able to recover at the original state. And why it descends? I think it is linked also to the cooling phase. We had some. There is this shift in the amount. There is a shift of membrane when the compression forces takes place. That I think was a bit hard for the secondary beam because I have to say it was, but I think it's really linked to this one. So we have there is this force of that asks the building to counter dilatate, and so there was additional compression in the full system beam plus secondary beam. Maybe this what create this increase of deflection or a sort of.
Yes. Good, thank you. Another question, this with the boundary conditions between the beam members in the mechanical analysis. So for example, between primary beams and secondary beams, are they sharing a node and sharing all degrees of freedom, or did you do something to model a simple pinned connection? And if yes or not, does that have an impact? Can you comment on those?
We tried first to make hinges between more specifically between the spandrel beams and the primary beams, but we finally at the time at least we went more into numerical issue than really having advantage of this kind of model. Then we saw that. When with the model that we have here, which is more fully rigid, we quite early we get the rotation that we will have expected in case of fire. So we generally prefer to keep the system more heavily connected than it really is, mostly for numerical reasons, but because in the end the overall behavior of the model was. We thought was correspond to reality anyway.
Thank you. There is a question about the fire scenarios. So you discussed quite extensively about how to define those, and with the sensitivity analysis, then you have the global fire, you have ASME. So that was very interesting. And somebody asked about traveling fire scenarios. And I would ask the question even more broadly. Can you comment a little bit on how you go about defining the scenarios and agreeing with the authorities having jurisdiction? And in Switzerland, is it common to maybe more recently also discuss traveling fire scenarios, or is this not something that is typically considered?
No. For the time of the project, it was 2015 or 16. Well, the Swiss authority is very pragmatic. So something that's really included in the codes in terms of models, just like the INGENI, for example, or the natural fire, it is directly considered. And what is not in the model, but still in a state of, let's say, literature research process or academic process, they would not want to get in touch with or accept this discussion. So at the time, the traveling file were, I would not say new, because there was already some huge works about the people working with this, but there was nothing in the codes that we apply in Switzerland. So because in Switzerland we use either the Swiss codes or the Euro codes, and so they weren't very keen on. This is why we stick to the fully engulfed fire, and we coupled it with the INGENI to localize to be more to be more severe in certain areas.
I see. Thank you. And so you mentioned this project's already a few years old. Did you see an evolution, or I mean, it's based on your response. I mean, it's whenever it comes to the codes, then the Swiss authorities start requiring it or asking about it. I guess that's how it would work.
But the evolution, no, there are some evolution, because, for example, at the time the guidelines were the one they comes from Luxembourg for facade, and there are now from 3-4 years, I think. There is a guideline Swiss that more or less are aligned with this one. And they also, at the time, they were very not keen at all with the FDS approach. And as Eric maybe showed, now there is an argument they can also be introduced in fair analysis more easily, at least. So I think they're quite evolving. There is the process of creating a code in Switzerland is. I wouldn't say that is long, but we are in this limbo situation that will be recently switched to the Eurocode. So we are not completely developing a full codes in some area of research, because we know that in a few years we will switch directly to the Eurocode. So as long as there's something which is very common in the Europe academic and norming institution, they more or less align with it.
Thank you. Okay, last question. Sorry, if you're still from Christian Malouk. He was asking about the ozone model for that compartment size. So for the ventilation conditions and size of the compartment, you went with a zone model. From your experience, is that the type of application, the type of dimensions you were dealing with, is that typical to use a zone, or have you seen validation studies, or was it a particularly large compartment?
No, I think the reason is linked to the fact that we have a very large compartment, and of course we are maybe beyond the limits of the ozone application, but because of course it may be a bit too large to where the real question is, can really have an engulfed situation in this kind of compartment, yes or no? So this is, but I think it's not so easy to answer. We had the open office. We know that more or less the thermal load is somehow, especially the new modern building, the office spaces thermal load is very low, because we already have very severe regulation about non-burnable elements that need to for the finishes, and that's it. So I think this is why I said we can use the engulf, because it's one scenario, at least it's one. You need to couple from localized scenarios as well that are very severe, special for columns or nodes or something else. And of course, you can use the traveling file model, which is now somehow accepted, even though I think it has also its limits. So I don't think there is, for the moment, there is a unique solution to this.
Thank you. Thanks a lot, Lorenzo, for this. I would agree. I think with file models, a robust approach is to to combine and run sensitivity analysis. Thank you very much, Lorenzo.